Shiva PNSK. In this class, we are discussing about the developments that are leads to the Bohr atomic model. Developments leads to Bohr atomic model. Here, the developments leads to the Bohr atomic model is taken. Previously, the historical results that are providing when electromagnetic radiation hitting the matter, then it provides some emission and absorption spectrums. Okay, emission and absorption spectrums. This is furtherly experimentally provided by Niels Bohr. Okay, Niels Bohr. Furtherly experimentally provided by Niels Bohr. Niels Bohr was developing the Rutherford atomic model, and then he is finding two properties which are nothing but one is the dual nature of a particle. Dual nature of a particle. When a radiation was moving in the electric and magnetic fields that producing the both particle nature and a wave nature. Okay, that is developed by Niels Bohr. And another one also spectrum, experimental results regarding the spectrum. Experimental results regarding the spectrum. These two things are leads to the developing of the Bohr's atomic model. Okay, let's see what the dual nature of the particle is here. Okay, firstly we will discuss the dual nature of the particle. In dual nature, the radiation possesses both wave nature and particle nature. Wave nature and particle nature. Okay. First we will discuss about the wave nature of the electromagnetic radiation. Okay. The wave nature of the electromagnetic radiation was introduced by Maxwell. James Clerk Maxwell in the year of 1870s. Okay, 1870s. Okay, he introduced that when an electromagnetic when a radiation is moving in electric field and magnetic field, that radiation producing the waves. Okay, that waves are in both electric and magnetic fields. This is the electric field. Consider this as the electric field, and another one is consider this as the magnetic field. Okay, here this is the magnetic field. Okay, this is the magnetic field, and this one is a electric field. This one is a electric field. Okay, this is the electric field. This is the magnetic field. This is the electric field and this one is the magnetic field. While moving the electric field and magnetic field waves, the waves are perpendicular to each other. They are moving with 90 degrees. Okay, if they are producing perpendicular here like this, okay, and opposite wave is moving like this one, okay. Let us see one example. Wait, students, I will show you the reference, the waves of electric waves and magnetic waves, completely electromagnetic wave which is perpendicular to its oscillating direction. Let us see. Okay, let's see. Assuming this is a electric field, okay, this is the electric field, this is the magnetic field. This motion is continuously occurring here, but in board we are representing this like here, representing this like this way, okay, but in moving it is in 3D. That's where we can't see here in the board 3D. That's why we are assuming that the both electric wave and magnetic wave are perpendicular to each other with 90 degrees. Okay, perpendicular to each other. Okay. Have you seen all this? Okay. By this, okay, you are seeing the visual observation of perpendicularity of the wave nature of waves, perpendicular of the waves of the electric wave and magnetic wave. Okay, by this he is proposing some properties. What are they? First one is, previously we are telling them, that is the oscillating charged particles of the electromagnetic wave is producing the radiation with perpendicular. Okay, both electric radiation and magnetic radiations are perpendicular to each other, and also they are perpendicular to the oscillating direction also. Okay, that is the first one. Electromagnetic radiations are perpendicular. Okay, next one. Unlike water waves, sound waves, these electromagnetic radiations not require any medium for oscillating. Okay, any medium for oscillating. They are freely moving in space also. Okay, they don't require any medium for oscillating. No medium is required. No medium is required. Okay. And third one, the moving speed of the electromagnetic wave is with velocity 3 into 10 power 8 meter per second. Meter per second. Meter per second. That much of speed these electromagnetic waves pass. Okay. During this, it produces some electromagnetic radiations. Okay. During this, it produces some electromagnetic radiations, which are that radiations are differed by some units called frequencies and wavelengths. Frequencies and wavelengths. Okay. What are that radiations? That radiations are nothing but X-rays, gamma rays, X-rays, microwave rays, ultraviolet rays, visible rays, and radar rays. Okay. You got my point? That radiations are differed by wavelengths and frequency. Let us see firstly what are the radiations are. Okay. Here the long radio waves. Okay, long radio waves. Let's see how they are. Okay. Here, let us come to electromagnetic radiation producing electromagnetic spectra. Okay, this is a EMR spectrum. Okay, this spectrum is differed by wavelengths. At the top, we are differentiating by frequency. Bottomly, we are differentiating by wavelength. Okay. Here, the spectrum is producing radio waves, microwaves, infrared waves, visible waves, and ultraviolet rays, X-rays and gamma rays. Okay. Here, long radio waves also there. Radio waves are producing with frequency 10 power 6 Hz, which are used in broadcasting and TVs also. Okay. Here, microwaves are ranging different. Here, microwaves are ranging around 10 power 10 frequency, 10 power 10 Hz, and these are used in the microwave ovens. Okay, and these are used in the microwave ovens. Let us come to infrared rays, nothing but IR rays. IR rays are ranging around 10 power 14. Okay, 10 power 14 Hz, and these are used in remote controls. Okay, let us come to visible rays. Visible rays are visible radiation. This part only we can see in the entire spectrum. Okay, because it is a range of 10 power 15 Hz. This part is only seen by our naked eye. Okay, seen by our naked eye. Because this radiation only appeared in the spectrum. Okay, the distance between the two successive crusts, the distance between the two successive crusts is called wavelength. Is called wavelength. The distance between the two successive crusts is called wavelength. Then what is the frequency? The number of waves produced per unit second. Okay, if electromagnetic radiation is produced in the time limit of second, how many waves are produced, which was telling by frequency. Frequency, which is denoted by nu, symbol nu. The wavelength is denoted by lambda. Okay. Here we are making some relationships between speed of the radiation or velocity of the radiation and a wavelength and frequency of the electromagnetic wave. Here lambda is the wavelength of the electromagnetic wave. Nu is the frequency of the electromagnetic wave. And c is the velocity of the electromagnetic wave, which is ranging nearly 3 into 10 power 8 meter per second. Okay, their relation is c equal to lambda into nu. Okay, then from this we are writing nu equal to c by lambda. If you finding the frequency, then we are using this formula. Okay? Let us see with some examples how frequency finding in the exams. Let us come to this problem. Here, the problem is taken from NCERT, which is the Vivid Bharati station of All India Radio Delhi broadcast on frequency of 1368 kHz. Okay, 1368 kHz. And calculate the lambda of nothing but the wavelength of electromagnetic radiation emitted by transmitter. Okay. There is one transmitter which emits the electromagnetic radiation with frequency 1368 kHz. Okay, he is asking finding the wavelength of that electromagnetic radiation. Okay, and also he is asking that one more, electromagnetic spectrum belongs to which range of the wavelength it is. Okay, wavelength it is. Let us see. What is the relation between what is the relation between wavelength and frequency? C equal to lambda into nu. Okay. What he is asking here, lambda. Then lambda equal to C by nu. Okay. C by nu. From that, the constant value of radiation is 3 into 10 power 8 Hz. Sorry, 3 into 10 power 8 meter per second. Okay, this is the constant value for velocity of the light. What is the mu here? 1368 kHz. 1368 kHz. Then convert this kHz into. Then we get this one also second inverse, then final we are getting a meter per second. Okay. This range is equal to the wavelength of the radio waves. This wavelength is equal to the wavelength of the radio waves. How are you telling that the range of radio wave is 10 power 0 to 10 power 3. Okay. Here is mentioning one more thing. Indian radio, all India radio, which is one of the broadcasting. In broadcasting, what we are using radio waves. That is a simple trick. Without finding this, we can telling like that also. From question also we are making the answer. Okay. Likewise, he is asking questions in the exams. Okay. Thank you.